Welcome to the Apron Academy. This video is specially designed for the dietitian in training, also known as the RD to be. In this video today, I'm going to be talking about niacin, which is also known as vitamin B3. Now, as I begin to expand my screen, you might be a little overwhelmed, and I don't want you to because I am going to explain everything. So, this big structure here, this big mechanism, that's what goes on inside of our bodies in order for our bodies to make NAD, but we'll get to that in a little more detailed a little later. What I want you to know right now is that niacin is a big umbrella term, but it actually has three smaller niacin molecules: this nicotinic acid, nicotinamide, and nicotinamide riboside. Now, I've made a special little star beside nicotinic acid because of something I want to tell you a little later in the video, but do keep this one in mind as we go forward. But you will see all three of these again, so just keep them in your mind. So when we intake niacin, we need it for multiple reasons, but I just want to say while we're looking at these three that many times we ingest in these forms, which that's great. We then will want to change these forms into the functional form, which I'm about to show you, but in fact, how about I just show you now? Dun dun dun! This is NAD. So NAD is the functional form or cofactor for niacin. NAD can be made from these three smaller molecules, but we can also ingest NAD in this form as we're eating our niacin. But in order for it to be absorbed, we do have to get it into these smaller molecules, kind of to get through the door of absorption almost. But then in order for it to function inside of our body, we need it to get back into this form. So we'll talk about how our bodies do that in just a second. But really, what is the big deal? I have life right here, but why do we need niacin for life? Well, here's some things that it does. It functions in glycolysis, fatty acid metabolism or catabolism, ketone body catabolism, and the catabolism of amino acids. So all of this leads to life. We need each of these functions in order to live. A fun fact is that we can get it from all of these different foods. Milk, beef, beans, peanuts, cereals. You can get it from poultry and fish as well. So how we absorb it is through passive diffusion. So right here. And now I want to talk about what it looks like in our body. So with passive, or in our body, we have niacin that comes in our body, it comes through our stomach, and it goes into the small intestine. So I want you to imagine that we're in the small intestine. So we are able to imagine that this is looking inside of our intestines. We're traveling through. You will see some microvilli. It will look a little different than my drawing, but you'll see some villi, and on these villi are enterocytes, which are the cell lining of our intestines. So we have the niacin traveling through our intestines. It is able to pass through these cells, pass through our intestines, and it goes out into the blood, which then goes into the liver to be detoxified, and then goes throughout all the body. So we need NAD in order to do all this. Now this, if you recall the very first structure, mechanism that I showed you, it was a little overwhelming. There was a lot going on there, but I really want to just simplify this and kind of explain what's going on. So first, I want to show you that we're going to talk about the kynurenine pathway, also known as the Denovo pathway. So I want to point out first that these are our three molecules. This is the nicotinic acid, nicotinamide, and nicotinamide riboside. So I talked about how each of these smaller molecules we need to make NAD. So this is showing how we can do that. So this will be the absorbed form. We have to get it back into functional form. So now I want to show you this kynurenine pathway, or the Denovo pathway. And now don't be alarmed when I do this. Okay, lots going on here. Let's explain it. So nicotinic acid is able to be converted into nicotinic acid mononucleotide. So it's adding a nucleotide on there. We have another enzyme that's adding another nucleotide, so we have dinucleotide. Nicotinic acid adenine is added on there, dinucleotide. Have another enzyme, and then it's finally made into NAD. So I just want to show you that with our little molecule, nicotinic acid, by a big, long mechanism, we are able to make this bigger molecule. So that's just the visual. So then you might be wondering, why do you have tryptophan? So this is one way that our body can make NAD itself. We don't have to ingest it like how we ingest it with these. Our body is able to have the tryptophan and produce NAD itself. We do need the rate-limiting enzyme IDO in order to do this. And so you might be asking, why don't we just make it ourselves? We don't have to worry about eating it. Well, it doesn't make enough NAD. We do need these other ways in order to make NAD, not just via the tryptophan and IDO. So now I want to show you another way that we can make NAD. We need to use these guys in order to make some more NAD. So here's another pathway, and I deleted my little line. This is called the salvage pathway. So we have nicotinamide. It's has this enzyme, turns into nicotinamide mononucleotide, have another enzyme, and then you have NAD. Nicotinamide riboside, there's an enzyme here that I just didn't write down, but turns into nicotinamide mononucleotide and then into NAD. So let me do this real quick. And I deleted lines again. But, so NAD is able to produce these enzymes. And these enzymes, I'm going to talk about them in a second, but for now you can look at this little guideline, but I will talk about it in a second. Each of these is able to produce nicotinamide. So when they produce the nicotinamide, it's able to go through this pathway all over again. That's why it's called the salvage pathway. NAD breaks off the nicotinamide. When it goes through each of these, nicotinamide is able to be reused, almost like a recycling. So now I think we're ready to move on. As you can see, it splits it up. Well, this pathway is our Denovo pathway. This pathway to make NAD is our salvage pathway. Alright, so now what we need to know is that NAD has two distinct functions. The first is that it acts as a cofactor for redox reactions, and the second is that it acts as a substrate for enzyme catalyzed reactions. So let's talk about this first function. Dun, dun, dun. Kind of crazy. But let's break it down. When NAD acts as a cofactor for these oxidation reduction reactions, it's gaining an electron and it's gaining a hydrogen. So then we see it as NADH. So you can see here where I have it all highlighted, NAD is being used in the Krebs cycle, so where we can make energy. It's being used in this electron transport chain, used in beta oxidation, so we're getting our fatty acids catabolized, and glycolysis, and also in this fatty acid elongation. So that's what NAD does in its first function as a cofactor for many of these redox reactions. As you can see, it's vital to life. We need niacin in order to function. Now let's talk about this second function, where it acts as a substrate in these enzyme-catalyzed reactions, regulating, so it regulates DNA repair and transcription through post-translational modification. So I want to point out that, so there are 4 of these enzymes, and they regulate the amount of NAD in our body. How do they do this? Well, the first 3 break down NAD in order to use it, and then the IDO synthesizes NAD. So, like we can see here, these 3 break down NAD to be able to act in this salvage pathway, and then IDO is able to create NAD, so it synthesizes it. I'm going to talk about PARP in just a second, but first I want to talk about these 3 a little bit. So the sirtuins is where it deacylases. That's the big word we need to know for sirtuins. It provides us health benefits and also life extension, so elongates our life. The CD38, I've shortened that. The name for it is ADP ribosyl cyclase. So the big thing here is chemotaxis. So it's sending our repair cells to the needed sites. So like if you have a paper cut in your right hand, you don't want all your cells to go to your left hand trying to help the paper cut. No, it's in your right hand. So the chemotaxis is sending it, these cells, where they need to go. And then we talked about IDO a little earlier when we were talking about that Denovo pathway synthesizing NAD. IDO is that rate-limiting enzyme in order to make NAD. It uses, it's the rate-limiting enzyme, and it controls the NAD by altering tryptophan concentrations. So now this can't always be turned on. It's a helpful enzyme, but if it's always turned on, then our tryptophan is always being used, and used for this pathway specifically. So IDO can't always be turned on, otherwise tryptophan wouldn't be able to go to all the other parts of the body and be used there. So we do not need this all the time. That's why we need each of those niacin molecules, like the nicotinic acid, nicotinamide riboside, in order to synthesize NAD, not just relying on the tryptophan with the IDO to make NAD. So each of these help NAD function as a substrate in these enzyme-catalyzed reactions to regulate the NAD levels, and then the NAD is able to regulate DNA repair and all that. So now let's specifically talk about the DNA repair. So PARP. This is our NAD, the big NAD molecule. in order to, I guess, use it for PARP, we need to break it down. So, glycohydrolase is the enzyme that helps break down our NAD into nicotinamide. So, just to kind of connect the dots here, NAD, we have NAD, PARP is breaking down the nicotinamide. Through this reaction, we're getting nicotinamide. So now we have PARP. Okay. Nicotinamide, and then we have this ADP ribose. So ADP ribose, this is how this is what attaches to target proteins via post-translational modification. So what does that mean? Let's talk in English. So we need this enzyme PARP. This is where the big thing comes into place. And I would write it all in here, but just so I can show you what's going on, I'll write it down at the bottom. So imagine this squiggly line is your DNA. On top of our DNA, we have histones, just going to symbolize that. Those are the histones. Each of these histones have tails. And then I'm going to take out my big, mean red pen, and right here, our DNA has been damaged. Oh no. So let's say you have been out in the sun, have that UV radiation, you have sunburn. So some of our cells are damaged because of the sun. So what niacin NAD is able to do is now this ADP ribose is able to attach onto the tails of the histones surrounding the damaged DNA, and it acts as like a red flag saying, come over here, this is where you need to repair the DNA. So we have all of this, these white flags coming on. Okay, so now let's say that we don't have enough NAD or niacin. We're not intaking enough. We are deficient. What does that mean? So when you get your sunburn, your DNA is damaged. Because you don't have enough niacin, you don't have enough to even start this reaction. So you don't have, take my big red pen out, you don't have this ADP. It's no longer there. The white flags aren't going up, or the red flags. The DNA is not getting repaired. It's not even getting signaled that it needs to go there. So we need niacin. We need niacin in order for our DNA repair. There we go. So now, moving on, we have pellagra. This is our primary deficiency disease. This is what happens if we don't have enough. It is, it presents with the 3 Ds, dermatitis, diarrhea, and dementia. So again, going back to what I just said, if you don't have enough niacin, then you're going to have skin problems because your body is not going to be able to get to those damaged skin cells and repair it. You'll have damage in your GI tract and even neurological damage. So now I just want to talk quickly about what do I do now as the dietitian. So as the dietitian today, B3 niacin is used to help lipid problems. So it helps treat high cholesterol. That nicotinic acid, so that's the very top molecule, small molecule that I had a little asterisk by. That's the only one of the 3 niacin molecules that works to treat these dyslipidemia high cholesterol problems. It's also, interestingly enough, the only one that causes flushing. Niacin can also be used as a treatment for genetic disorders. So I hope this video helps you. I hope you're able to see that niacin is important to life, and also that we need this, and that you're able to see that we can break down these different mechanisms and help it to be more understandable. If you enjoyed this, please like this video, subscribe, and thanks for joining me.